the electromagnetic radiation, such as light, is a form of energy. So the electromagnetic radiation is a form of energy, like light. It represents a form of energy. And this energy propagates through space as electromagnetic waves. As we can see here, the electromagnetic waves, it is composed of two components that are the magnetic field and the electric field. Both they oscillate in space in two perpendicular planes. And it is important to talk about the properties of these waves. So a wave, we have different types of waves. We have water waves, sound waves, and light waves. But we are more interested in the light waves. So a wave is characterized by these properties. It has a speed, that it has a symbol of c. It has also a frequency. It has this symbol, nu, and it has also a wavelength, lambda, and it has also an amplitude. Let's say A. So the speed, what is the speed of the wave? It is the covered distance by unit time. It is a distance by unit time. The frequency is the number of waves that pass through a given point in 1 second. The wavelength is the length between, it is the distance between two identical points from two successive waves, and the amplitude, as we can see here, it is the vertical lines between the midline and the peak of the wave. So we have all this. So the wavelength, it is the distance between two identical points. So here it is a distance in meter, for example, or in another distance in it, for example, nanometer and so forth. So, and these three quantities, the speed, the frequency, and the wavelength, they are linked by this expression, which is c is equal to lambda times nu. And here we have the wavelength is given in as a distance, so in meter, and the frequency, it is the number of waves that pass through a given point in 1 second. So it is the number of waves per second. And here we got the unit of the speed of light, which is in meter per second. And the speed of the electromagnetic radiation, it is a universal constant. It is a universal constant which has a value of about 3.0 times 10 to 8 meter per second. It is the value of the speed of the electromagnetic radiation or of the light in vacuum. But the frequency and the wavelength can have different values. So only the speed of the radiation, of the electromagnetic radiation, that has a universal constant, but the frequency and the lambda can have different values. Also, if we do the comparison between these two waves, we can notice that the first one in A, it has a longer wavelength, and in B, it has a shorter wavelength. So we can see that in A, we have a lambda A, it has a longer value than the lambda B. But if we observe the frequency, the number of waves that pass through a point in 1 second, we can see that the second wave, it has a greater frequency. So we can say that the frequency of A is smaller than the frequency of B. So we can see that the relationship between the lambda and frequency is inversely proportional. So lambda is inversely proportional to frequency. Now let's talk about the types of the electromagnetic radiation. So the various types of the electromagnetic radiation, all they have the same speed. So all the electromagnetic radiation, they have the same speed because it is a universal constant, c. But they differ in their wavelength and frequency. So they have the same speed but different frequency and wavelength. Here we can see the different region of the electromagnetic radiation. The visible region, it is the region which our eye can detect. It is composed of all the color in the visible spectrum. So it ranges from 400 nanometers to 700 nanometers. And here we can see that on the left of the visible region we have the high energy radiation, that are the ultraviolet, X-rays and gamma rays. And on its right side we have the low energy radiations, that are the infrared, microwave and radio waves. The scale A is given for the wavelength and the B represent the frequency. So we can see here that by moving to the right side the wavelength increases, and when we see for the frequency for the B, we can notice that when moving to the right side the frequency decreases and on the left side it increases. So it is opposite to the wavelength. Now let's do this first example. We have, for the first question, we have the bright reds of fireworks, that they are due to the emission of light with a wavelength close to 650 nanometers. So we are asked to calculate the frequency of this red light. So we have here example 1. We have a red light. So it is this red light, it is due to this emission. That has this emission, it has a wavelength equivalent to 650 nanometers. It is responsible of the bright red lines from the fireworks. We are asked to calculate its frequency. So the link between the wavelength and the frequency is the speed of the electromagnetic radiation. That is written like this: lambda times frequency. In order to calculate the frequency, we have to divide the speed over the wavelength. So now we replace. We said that the speed of light, it is a universal constant that is equal to about 3.0 times 10 to plus 8 meter per second. And the wavelength here, it has a value of 650 nanometers. But here we can see that we cannot consider nanometers with meters, so we have to multiply by a conversion factor. We know that 1 nanometer is equal to 10 to negative 9 meters. So we multiply by this conversion factor, 1 nanometer, and above we have 10 minus negative 9 meters. So we can here consider nanometers with nanometers, meters and meters. At the end we get a value in second to the negative 1. And by making the calculation we get a value of 4.62 times 10 to 14 second negative 1. Or we can use the unit of hertz. 1 hertz is equal to 1 second to the negative 1. It's the same thing. The second question, a radar gun operates at a frequency of 35.5 gigahertz. What is the wavelength of the radiation emitted by this radar gun? So here the same thing, we use this relationship, but but this time we'll calculate the wavelength because the frequency is given. So the wavelength of this radar gun, so it is C over the frequency. It is equal to, again, 3.0 times 10 to 8 meter second minus 1, and it operates in, it has a value of 35.5 gigahertz. Here we have to convert to hertz, because 1 gigahertz is equal to 10 to plus 9 hertz. So we multiply by, so 1 GHz 10 hertz. And also we know that 1 hertz is equal to 1 second to the negative 1. So we can cancel here gigahertz with gigahertz, hertz with hertz, and second to the negative 1 with second to the negative 1. We get a value in meter. But in meter it is a very small value, so we can convert to millimeters and we can get the value of 8.45 millimeters. So here is the wavelength of this radar gun that operates at this frequency.